Okay, so this is lab 3 and part 1 where we are making a sequence circuit, and this is the state diagram. And we got the state diagram by first looking at the schematic and finding the relative inputs required for the FF input equation. So for JA, B goes into it. KA is constantly 1, KB is constantly 1. Input through JB is A naught, and DC is an XOR of C and B. So this is how we made the next state, acknowledging the laws for the D flip-flop and the JK flip-flop, whereas the output for D would follow, the output for D, which is Q, would follow D, while the output for the JK flip-flop would follow JK, where J is set and K is reset. So when making this circuit, we have to make sure that the clock input for the D flip-flop is at a high state, because the D flip-flop only changes when the clock is at a high edge, while for the JK it only changes when the clock is at a low edge. And that's why we use the XOR over here, so that the input in the JK is both a low edge from the clock input, making sure that the output from the JK flip-flop is constantly changing to the input. So now here I made sure the synchronous reset direct input for the JK, for the D flip-flop rather, was high because it's active low, as with the JK flip-flop. And I also made sure the asynchronous, I don't know what it's called, but it had to be, it's active low for the JK flip-flop, so we had to make sure it's high. So we connected it to VCC. Okay, so now onto the circuit board. Now, as you can see from the state diagram, the transient states can be seen, which is 0, 1, 1 and 1, 1, 1. That's 0, 1, 1. You hold it. I'll just show this. 1, 1, 1 and 0, 0, 0. And these are the transient states. And the reason they're showing is because KB and KA is low. But if KA and KB are both high, you'll see the state diagram starting to, you see it goes to 0, 0, 1, 1, 0, 0, 1, 0, 0, 0, 0, 1, 0, and this follows the state diagram. Just show the state diagram, the lights together. Here the state diagram is followed.
Can I have your availability?
Now this is the part 2 of lab 3, and in this we have to construct 3 circuits and we have to demonstrate 2 of them. So the 3 circuits you can see here are the light chaser, the part 2 using a 8-to-1 multiplexer and a single gate, and the third circuit, which is using a 1-to-8 decoder and a single gate. But we're going to demonstrate the light chaser and the 1-to-8 decoder and single gate. So let's start with the light chaser. Now, looking at the data sheet for the decoder, we can see that when the input is 0, which is low for the 3 inputs, you can see the outputs are going to produce a high besides the Y0, which is going to produce a low. But when the counter increases the number to 1, you can see that the second output is going to be low, and that carries on for every number that's increased. When it's 3, the third output becomes low. When it's 4, the fourth output becomes low. And you can see how the sequence occurs for a light chaser. So the demonstration is here, and you can see we've drawn the circuit on the board, and you can look at the output. When the input is 8, it's low. Now it's 2, 3, 4, 5, 6, 7, 8, and this is how the light chaser is produced.
So this is part 2. We're using an 8-input multiplexer and an AND gate in order to display these values in 4-bit binary code. Now these four buttons represent the binary code, and we'll be showing it to you from 1 up to 14. So this is 1, 2, 4, and 8. This is 3. This is 4. This is 5, this is 6, This is 7, shouldn't be lighting up. 8, 9, 10, 11, 12, 13, and 14.
Just do 12 again.
This is 12.
12 is 1100. 1100.
Yeah, 1100.
Not lighting up.
It's not lighting up.
12 is not output. Okay.
Okay.
And just to add on how we figured out the I0 to I7 by looking at the F output and comparing it with the D input values, we can see that F for this first two inputs is 0 0, which is representing I0 as 0, while for this second section D is 0 1, F is 0 1, which is representing D. And for example, I3, when D is 0 1, F is 1 0, which is representing D naught. This is how we made the inputs for I0 to I7, and it corresponds with this function table. This is lab 3 and part 3, and in this we're going to show a static one hazard using this schematic. We've drawn the K-map, and the static occurs in this transition when it goes from 110 to 101. So leaving A and C constant at 1, we're going to be changing B from 1 to 0, and we're going to use a clock for that using this. And as you can see in the oscilloscope, you can see a static 1 hazard. From when it goes from 111 to 101, there's a static 1 hazard. For a millisecond it goes to 0 and comes back to 1. And now this is the solution for the static 1 hazard. What we did is we added another NAND gate of AC, connecting it to a 3-input NAND gate, and we added 2 more inverters over here. And as you can see, there is no more static 1 hazard. Output is no more going to 0 for a split second. And the reason why it's constantly 1 is because, as you can see here, when the input is 111, the output is 1. When the input is 101, the output is 1. Hence, it's a constant 1. And this concludes part 3 of lab 3.